Hi, it is the second part of section 3.8, derivatives of logarithmic functions. Okay, here fx is log ax, then it is the same as x equal a to the y. Now, a to the y can be written in this way: exponential function with e and natural logarithm. These two inverse each other, so it's an identity function. So we can write in this way, like over there, for x is positive, then x is same as e to the natural logarithm of x. Exactly here now, we can write in this way. Now, by using the power law of logarithm, y can be here in front of a logarithm. Okay, now we are applying the implicit differentiation or chain rule. Anyway, we apply the differentiation with respect to x. Then that will become 1. And here, first we consider y logarithm a is a variable u. Then here now, that is e to the u, and u x derivative, which is same as y prime logarithm a. Now we solve it for y prime. Then here y prime is same as 1 over e to the y logarithm a and natural logarithm of a. Now e to the y natural logarithm a is the same as x, so that we eliminate terms including y here, so that becomes x. So y prime is same as 1 over x logarithm a. We can summarize here. So the derivative of log ax is same as 1 over x logarithm a. This is a special case. Now, natural logarithm has base e, so that here natural logarithm of e is 1. So here we don't have any extra term. So this is a special case of this general derivative. Now, for exponential function, here if we make a derivative, then that is just simply logarithm a is multiplied. Earlier, when we tried to get derivative of a to the x, that is basically this position is the same as now f prime at 0. We did. Let's go back to that position here. Okay, around here. And if fx is a to the x, then by using the definition, and we can get the derivative, and that is same as a to the x and f prime at 0, right? But that one is now explicitly here. This term is the same as, now that is natural logarithm of a, right? Okay. Now here, we go back to the position, and we'll prove this one later below in example 3.64. Once we admit this formula, then this formula is a special case. Here, again, logarithm e is same as 1, so that here we don't see the extra term. So once a is e, then we have to have that formula. So that is a special case. Now, for logarithm, here fx, rather than x, just a general function is given, then the formula said that is f prime over f. The reason is, anyway, for that one, okay, by using here chain rule, we can reach it here now. That is same as, okay, d logarithm of f over df times df and dx. So for f is now variable and differentiate with respect x with respect f, so that here that'll be 1 over f, and now that is same as f prime, so we can write here f prime over f, right? So that is the formula. And for this one, now we already know that x is positive, then already here 1 over x. And once x is negative, then now here logarithm x will become here logarithm minus x. Okay. If we differentiate it, then first we consider the variable minus x, so that we differentiate this one with respect to minus x, then that'll be 1 over minus x. And here the minus x must be differentiated with respect to x, which is minus 1, so that is same as 1 over x. So here with absolute value, logarithm of x absolute value, and that is the same as 1 over x. This is a generalization of that formula. Right? Okay. Now we will differentiate the function f is given x to the x, and x is positive. Then x to the x can be written again along with that identity function. We put here x to the x, and by using power rule, and x will go in front of logarithm. Now we are making the derivative here, x to the x prime, x derivative will be the same as, first we'll try to make here derivative with respect to that variable. Now this is u variable, then the same as e to the x logarithm x, and here we have to multiply x logarithm x and x derivative, right? Okay, this one is the same as, now here by using product rule, and that is same as logarithm x plus x times 1 over x, which is same as natural logarithm x plus 1. So we can conclude here now the answer in this way, e to the x. Now, okay, e to the x logarithm x and times here logarithm x plus 1. However, this term is the same as originally here x to the x, so that here we have x to the x, and that is logarithm x plus 1. Okay, that is the final answer. You can do in this way, or okay, we can do another way, which is called logarithmic differentiation. We learn later on. But anyway, we start with y equal x to the x. Now we apply both sides natural logarithm. Then logarithm y equals same as logarithm x to the x. By using power rule, we have x logarithm x. Now we are making implicit differentiation, which is an application of chain rule. That is now here. We already know that here. Now logarithm f of x, then the derivative will be same as f prime over f. Now there is y as a function of x, so that derivative with respect to x will make y prime over y. And right side, that is derivative of x by using product rule. We have logarithm x plus x times 1 of x So that there is now here natural logarithm x plus 1. So we can conclude here y prime equal y times and natural logarithm x plus 1. What is y? Y is already x to the x, so that we can reach at the same conclusion, which is now x to the x and natural logarithm x plus 1, right? Okay, you can apply logarithm, natural logarithm both sides, and then you can just make some the implicit differentiation or chain rule, and then solve for y prime. And once y appear, then replaced by the function. Okay. Okay, now we'll try to find the derivative of the following. Okay, here, part A. Okay, now y prime equal logarithm of fx, which is same as f prime over f. F prime is now 6 of x, and then now f itself is 3x squared. So you can simplify. Okay, now part B. Okay, g of x is the same as now logarithm x to the half power. So when you try to get g prime, then we consider this one as a variable, then half will go out and logarithm of x and minus half power, and derivative of logarithm x, 1 over x. Right? Then here now that is 1 over and 2x and square root of now logarithm x. That's the final answer. Okay, now again for C, you can do it quite easily, exactly the same way as for that one. Now also for this one, you can do it the same way, but we'll try a little bit different way. Now that natural logarithm is by using the sum formula, we can write this one logarithm 3 plus logarithm t and plus logarithm, natural logarithm e to the minus t. Now, that is same as natural logarithm of 3 plus natural logarithm of t. Now, plus here, okay, natural logarithm e and power minus t will go out. Okay. Oops, here minus t will go out, and then logarithm e will be 1, right? So that's it. So here y prime will be, for that one, it'll become 0, that will become 1 over t, and there's minus t, so it's minus 1. So answer for part D is 1 over t minus 1. Okay, quite simple. So once you try to use logarithm rule, then the properties of logarithm, then you can get the solution much more easily. There's again this example. Here, inside logarithm, we have half power, so that inside this bracket, that is same as, now let's try to manipulate here. There's half power can go out, and there's a logarithm x plus 1 to the 10 divided by here 2x plus 1 fifth power. Because the whole thing here, okay, originally that is whole thing, that one half power, that half it go out here. Okay. Okay. Now from here again we use the property. Now that is a subtraction property. So that same as half is there, and here logarithm and x plus 1 to the 10 power minus natural logarithm and 2x plus 1 fifth power. Again, we can use one more time the logarithm property here. 10, the power rule, 10 go out, 10 times logarithm here x plus 1 minus the same a 5 times natural logarithm, now 3x plus 1. Okay, so now that is basically y, and then if we try to get y prime, then here and with the same coefficients there, and then 10 times. And for this term, now x plus 1 is a variable, then there is x plus 1, and x plus 1 derivative is 1. Okay, we consider this one as f of x, so that derivative of that term is 1, and f of x is x plus 1. Okay, now minus 5, and the same derivative of that term is 2, and now this is 2x plus 1. If you want, then you can simplify, but anyway, this is a solution. And from the previous example, we see that using the properties of logarithms prior to differentiation may simplify our derivatives overall. Yeah, you can get derivative much more easily by using the properties of logarithms. Now we try to use the natural logarithm, particularly here the natural logarithm, to manipulate particularly the products and powers when we try to get derivatives. Here, this is the strategy, and take natural logarithm in both sides, and then here we use lots of logarithms, and now differentiate implicitly with respect to x and solve for y prime, and fx must be replaced by, y must be replaced by f of x. Okay. Now, here in this problem, fx is given a to the x. Now, use logarithmic differentiation to prove that one. That is here appearing here. And a to the x differentiation is same as a to the x times logarithm a. Okay, we'll prove that. Okay. And start with this one. And even though it is given f of x equal a to the x, now you start with that writing. Like when you try to find the inverse of function, then fx is given, then you start with y equal fx, and now solve for x and exchange x and y. Exactly the same, you start with y equal a to the x and apply now logarithm both sides, then natural logarithm a to the x, which is same as x natural logarithm of a by using power law. And now we differentiate with respect to x, then there's a function of x, so that y prime over y, f prime divided by f. Okay. Now we have only this is constant and x term, so the derivative of x is 1, so that we have just constant logarithm a. So we can reach here y prime. Now we here solve for y prime. So that is now here y and logarithm a. And what is y? Y is a to the x, and that's a logarithm a. We proved that, right? Okay. Use logarithmic differentiation to find the derivative of the function. Quite simple here. Again, we apply natural logarithm. Then there is natural logarithm x plus 1 to the x. Now power rho makes here x times natural logarithm x plus 1. Now we differentiate it with respect to x. Then there's y prime over y equal, now here product rule, then there's a natural logarithm x plus 1 and plus now x, okay, times, now there's f of x, so that f prime is 1 divided by f x plus 1. So you may simplify it like a natural logarithm x plus 1 and plus x over x plus 1. So here we can get y prime equal y. Y is now x plus 1 to the x. So that we write down here that is x plus 1 to the x. And here we have a natural logarithm x plus 1 plus x over x plus 1. Okay, this is the final answer. Now for this problem, same we have here natural logarithm of y equal same as natural logarithm of that term. Now that is power, so that natural logarithm x will go out, and that is natural logarithm of sine x. Right? Now we differentiate both side with respect to x. Then here left hand side will be y prime over y. This is a function of x, so that now so that f prime over f exactly here. Now we are using product rule. So first this one is 1 over x and logarithm sine x and plus here logarithm x and derivative of that. Okay, derivative of this term is, now this is f of x, so that f on the bottom, top f prime is cosine x. Right? Okay, so here now we have y prime equal y times that term. Y is here sine x to the logarithm x times that whole thing. And here natural logarithm of sine x over x from the first one. And now second one is now natural logarithm of x times that is basically cotangent, but we write down here the same cosine x over sine x, and like that. That's the final answer. It's a little bit complicated, however, quite mechanical. So that by using the technique you are doing, you solve the problem almost the same way. Okay. Now here, for the number e, we have another interpretation. That is same as here now, as x approaches 0 is a limit of the here 1 plus x and 1 over x. Here, this one is approaching 0, and that one is reciprocal of that one. And there is e. Now we'll prove here. Okay, let's begin with logarithm x. Then the derivative of logarithm x is 1 over x, and at 1 the derivative will be 1. We know that, so we'll use this one. Now f prime 1 for that function, we are using the definition. So that is same as the quotient f 1 plus h minus f1 over h, and limit h approaches 0. That is definition of derivative at 1. Now, okay, for that one, here, now that is, originally we defined this way, but rather than h notation, we may use x notation, no problem, right? So here, everywhere h is replaced by x. Okay, then, and here, 1 of x here, now f1 plus x is now logarithm 1 plus x, and then f1 is logarithm 1, which is 0, so we reach at that one. By using the power rule, and 1 of x can go here as power. So we reach at that one, limit x approaches logarithm, and here 1 plus x and 1 of x. Now, the logarithm function is continuous so that we can change the order. So earlier when we learned continuity, and we learned that for continuous function, limit and continuity are commutative. We learned that. We'll use that here. So logarithm next, first here, limit. Okay, so we reach that form, but this whole thing must be 1. F prime at 1 equals 1 must be 1. That means that now logarithm, this whole thing is 1, means this whole thing must be e. So logarithm, natural logarithm e is 1. So this must be e. So we have here conclusion e can be interpreted, calculated by using that. So, we try to use x smaller, 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 and with that, the here now 1 of x power, then the value is approaching e. This formula can be written in this way. Here, now we change here now, for example, now n goes to infinity, but if we here change a variable, x is 1 over n, then n goes to infinity is the same as x goes to 0, and 1 over n will be x here, and n will be 1 over x, so that eventually this term and that term will be the same. So e, the number e, can be also expressed by this limit, either this way or that way. Okay, that is the end of the section. Thank you.